Okay, let's wrap up the lecture now. What I wanted to do was talk to you a little bit about some of the giants in the field. John von Neumann, he was a cyberneticist who worked on the ENIAC, and he came up with his own computer called the EDSAC. EDSAC was installed over in the Institute of Advanced Studies at Princeton, and ENIAC was over at the Moore Electrical Engineering School in University of Pennsylvania. Gabor was really a mathematician, and he advocated the windowed Fourier transform. With wavelets, we start to come up with elements that allow us to get basis functions. One of the basis functions that I was working with, the Gabor transform, uses a sine wave that's been superimposed onto a Gaussian waveform. So what you do is close your eyes and picture the Gaussian hat with a little lump, and then on top of that superimpose sine waves, and that's your Gabor transform. Some people will call that a sinc function. You can do that in 3D, by the way. That's why they call it the Mexican hat filter. With the Mexican hat filter, you can change the peak of the Gaussian hat, you can change the frequencies, and you can shift the phase. And this allows you to isolate various waveforms and their in sub-pixel resolution when you're going for edges. The Haar transform is a little bit simpler. It kind of looks like a bunch of square waves. You know, that Haar transform, if you think about it, really sort of lends itself to a kind of digital design approach. And in fact, one that there is a transform just like the Haar transform, a series of basis functions that can be generated completely digitally. And it's called the Walsh transform. And with the Walsh transform, it's just like the Haar transform, only with a difference, and the difference is you can generate it with an FPGA if you like, or with a sequence involving TTL. And there's the Mexican hat wavelet function. Some people call it the Laplacian of the Gaussian. And I've seen abbreviations for it called log, or log filters, Laplacian of Gaussian filters. And here's your discrete wavelet transform being used for reconstruction on an arbitrary function. Here's the complex function in here. Here's a bunch of Haar basis functions, and here is the relative sum of the different Haar basis functions. And you can see we're starting to get close to an approximation. And you can compare that with the approximation that you had prior. This is the Fourier transform approximation. It's much smoother. Now look at the discrete wavelet transform approximation, and you can see all the little square wave edges coming through. What I'd like to do now is skip ahead, skip through the singular value decomposition. We've already talked about the drawbacks. Well, here's a big question. Which is faster? The fast Fourier transform or the wavelet transform? Well, I don't know if you remember, but the fast Fourier transform is built on this idea that you're going to work on all of the odd samples and then work on all of the even samples. And you take that subset of the odd and even samples, and you recursively subdivide them into odd and even samples of the odd samples, so it becomes odd, 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 even, and the odd, even samples of the even samples, so it becomes even, odd, even, even, and you keep going. Well, with the Fourier transform, you got recursive subdivision working for you. and that enables you to divide and conquer your input sequence until it keeps getting shorter and shorter by half each time. And that's kind of a big win. That's what makes it fast. So you can implement the fast Fourier transform using recursion. Well, you can do the same thing with the wavelet transform. Because of the decimation, because you're shortening the sample set each time, it becomes, instead of odd even, it becomes low pass, high pass, and then low pass, low pass, low pass, high pass, and then high pass, low pass, high pass, high pass. And then that keeps getting shorter and shorter in length. And so what you get from that is another mechanism for doing a very fast transform. So discrete wavelet transforms are just as fast computationally as fast Fourier transforms, in theory. You can have continuous wavelet transforms and discrete wavelet transforms, just like you can have discrete Fourier transforms or analog Fourier transforms. Either is available to you. Let's see if there's anything here we need to discuss. Talked about the wavelets. Here's a Haar wavelet. Let's see now. What else we got? We saw the continuous transforms. I think what we're going to do is skip ahead to applications. Let's do an application. So, suppose you said to me, well, gee, what does it sound like if we do one of these low-pass filters to an audio signal? These are time domain convolution filters, right? So let's try one. I'll do an implementation of a low-pass filter. Oh, here's some filters. Here's a bandpass filter. Let's do a low-pass filter. New Java class low-pass. So for my low-pass filter, public static void main, Control-J, enter. I will read in an input signal. Let's see now. U law codec ULC equals new U law codec. Now, why is he giving me a hard time here? Does that need to be lowercase? Yeah. No? I really don't know why he was giving me a hard time about that, because that is correct. So then what we'll do is we'll do a double double equals double D array equals ulc dot get double data ulc dot play and what I'd like to do is just sort of open up a file and hear it. So that seems to work. Now the ULAW data codec says here he can take a file. So what I'm going to do is I'm going to provide it with a file name, feudal.getReadFile. Select an AU file, and then what's he on about? Have to import it? Okay. And this will give me a file name. seems to want to interrupt my programming flow at every turn, but that's alright. And now what we'll do is we'll print out the file name, and then we'll use that file for our input. And there's a method to my madness. The reason I'm doing this is so I don't have to have a file open dialog box every time I want to run my program. So let's try this Techno machine again. And here's a fully qualified path name, which I shall copy and insert directly into my code. So what I'll do here is I'll say the file is equal to new file of, end quote, paste, and you can see the IntelliJ system has put in the double backslashes to escape the backslash that's natural for DOS. So now I can avoid the standard file open dialog box that you're getting every time you run the program, and you should just hear it. And later I figure if I want to, move this program to another computer where the paths are different, you'll uncomment the part where you get the read file, and it'll allow you to navigate to the correct location. Does that sort of make sense to people? It's just a convenience for me because I can't, wear out my wrists navigating through a file system every time. So now what I'm going to do is I'm going to do my little low-pass filter doodad. And so, how does this work? Well, let's see. Double filtered data is equal to double of d.length. Oh, I guess you need a new statement, right? And then we'll write a little for loop, integer I, 0, while I is less than d.length, I++. And then what we wanted to do here was filter of I equals d of I plus d of I, plus 1, and I can see right away where there's going to be an error. It'll go off the end of the array, right? So I'll have to do something about that. Perhaps I should say -1 so it doesn't go beyond d length plus 1. And then I gotta make a new ULaw codec? I think I do. Now he says here he'll take a linear array of doubles, so I'll put in the filtered data, and then what we'll do is we'll play the low-pass filtered code. What do you think of that? That sort of look like it might work? Oh, ye of little faith. So that worked. As a matter of fact, you could probably take this whole section in here and call it LP1. So we'll extract it into a method, call it LP1. Okay. And now we've got a cute little mechanism by which we can call LP1 multiple times. And I could call LP1 of LP1, where LP1 is going to make a copy of the double data and form the average. So we can do this multiple times, recursively, as many times as we like. So what would happen if we did this, I don't know, a bunch of times? What would be a good way to do that? Like a for loop, maybe? For integer I equals 0 while I is less than 9, I plus plus. We got filter data in here somewheres. Oh no, we don't. We can just say D equals. How's that? Just overwrite it. And then do it like 9 times. I think you need a semicolon here. And then I guess one last time. What do you think of that? There's like a return statement here. And this will be the average of adjacent numbers. So I'm thinking we've got a nice low pass filter here. I really wanted to hear this become muddy, and it is. I mean, that's like a 90 pole filter here, giving us only the low pass values. Let's cut that in half. Can you hear it? So it's making a difference, right? Let's do that again. Right? You can hear it. So it's great fun, low pass filter using averaging, and that's giving us half of the Haar transform without the lifting, right? Because this is not integer computation. Fun, right? Very fun. So much fun. How much fun is it? Lots of fun. Okay, how about this? How about if we create a filter that does more than low pass filter, it also decimates. Right? And the decimation filter, well, let's see now. We can do that. Public static double what shall we call this? Decimate? And pass in a double D array, and I like my array elements to be after the variable you pass in. I don't know why IntelliJ insists on doing it the other way. And now I can sort of cut the size of the array in half by decimation. I'll take every other element. That's like a for loop, right? For integer I equals 0 while I is less than d dot length on 2. Actually, can't I just say I equals I plus 2? D dot length I equals I plus 2. And what we'll do is we'll establish an output double out array equals d dot length on 2. Oh, I need a new statement. New double array d dot length of 2. And now what we'll do is we'll devise a new increment. How about integer k equals 0. So out of k equals the input d of I. And then we'll say k equals k plus 1. So we can see we'll keep going through. We could have said k plus plus, right? But I like this better because it shows that we've got k starting with 0. Out of k keeps incrementing more slowly than d of I, which goes twice as fast. And so this is resampling the input signal and causing 2-to-1 decimation, which is what the 2 with the down arrow is supposed to mean. So this does arbitrary 2-to-1 decimation of any input signal, cutting it in half. And then at the end of the day, you have to return the decimated signal. Got that? Want to test it? Sure, let's test it. How do we test a decimation? We need something not main. How about this? We'll do, this will be the low pass filter test. So we'll extract that and we'll give it a name and call it low pass filter test. Okay, that's a very fine idea. And then what we'll do is we'll make up some sample data. Give me some numbers. 1, 2, 3, 4, 5, 6. Is that good? 7, 8. I'm just making this up, okay? And then what we'll do is we'll print it. Print utils.print of A. Alt enter. And then what we'll do is we'll decimate it. A equals decimate of A. And then what we'll do is we'll print it again. Print utils print of A. So before and after decimation. Got that? Alright, so what do we expect to see? 1, 3, 5, 7. And hopefully it's not going to throw an arithmetic exception at runtime. No, what is it? An array out of bounds at runtime because I miscomputed one of my for loops or something. Oh, there it is. 1, 3, 5, 7. Yeah, that looks like decimation to me. Right? Does that look like decimation to you? It's what you'd expect. So now let's do the averaging thing. What we'll do before, that is prior to decimation, is we'll say A equals low pass of A. So first we'll low pass filter, then we'll decimate. What do you get? That's pretty cool. So instead of 1, 3, 5, 7, it's 1.5, 3.5, 5.5, 7.5. Right? Kind of what you'd expect. So in effect, if I knew the differences between 1 and 2 and 3 and 2 and 3 and 3 and 4, I could encode those. That's the high pass side, and then I could have the low pass side and the high pass side together and transmit those two numbers and do a reconstruction. Got that? Cool, right? So now let's assume that we're sort of happy with this, and it's I'll call it my decimation test. So now I got a decimation test, I got a low-pass filter test. Let's go back to this low-pass filter test. Now suppose after the low-pass filter you do a decimation. So here it says low-pass filter, and then after low-pass filter I do decimate. And I don't know if you noticed, I'm using functional programming, so low-pass filter may create some extra storage, but the life of that storage is very limited in scope. So as soon as it returns and is passed into decimate, and decimate then returns, the extra storage doesn't effectively have to last for very long, because decimate makes something that's half the size. So even though you're calling this 22 times, it keeps getting smaller and smaller, until eventually there's not going to be much left. So maybe what we ought to do is just call it like once or twice. And now when we play it, it's going to sound really different, because we are increasing in frequency. Oh, array arithmetic out of bounds, blah blah blah. I think we have to truncate to integral power of 2 on this one. Right? So that's the low-pass filtered part. Decimated means you're going to have fewer samples, so it goes by much faster. Let's change that to just one run of decimation. So it's still recognizable, but it's going by much faster. And it hasn't changed in pitch at all, because we did the low-pass filter. Yes, sir.
Can you explain the truncate to integral power of 2?
Oh, right, truncate. What this is doing here is it's truncating D so that it's an integral power of 2. So let's see if we can look at D prior to the truncation. S out, Control J, enter, quote, D dot length equals end quote plus D dot length, and then n paren sem, and then what we'll do is truncate to a integral power of 2, and that will mean that the decimation, where we keep cutting things in half, won't cause us to have an array out of bounds exception at runtime, because what I'm doing is I'm making sure that 2 to the n elements, like here 32,768, is exactly an integral power of 2. It's probably like 2 to the 15 or something, right? So because 2 to the 16 is 65,536, that's a little bit larger than 49,000. So I truncated to 2 to the 15, 32,768, and thereby made it so that when I want to do the let's say a fast Fourier transform, or in my case a decimation by 2 operation, I'm not going to have the arithmetic out of bounds exception at runtime. So I guess I could have done it a couple of ways. I could have padded out the signal with extra zeros to bring it up to 65,536, which would be 2 to the 16. But instead what I did was I chose to truncate the difference between 49,315 samples and 32,768 samples, and I just chopped them off. And that way, when I do my decimation, I don't have to worry about the exceptions. Does that make sense? Because when you're taking every other thing and you're incrementing by 2, you have to have an integral power of 2 samples because of my boneheaded simple algorithm. That's BHSA, boneheaded simple algorithm. Right? Perhaps we could call it boneheaded simple algorithm version 2.0. so when we publish it, we'll all know what it stands for. Also have another one called DDBF. Algorithm DDBF, that's Doug's algorithm, Doug's dumb brute force algorithm. Oh yeah, we need the A in there. Dumb brute force algorithm. Algorithm DBFA. Dumb brute force algorithm. Or Doug's dumb brute force algorithm. DDBFA. Version 1.1. I'll put the .1 in there just so that people will know that we've been working on it. So what do you think? Right? It's real. I'll call it simple kinds of local image signal processing. What's local about it? Because if you're streaming this kind of an image signal processing, right, is very easy to do as the signal comes in. You only need 2 samples in your buffer, and then you can produce another sample immediately on the output. And this is real. This can be done in real time. As the signal comes in, you can do some simple operation and then pass it straight out again. You don't have to store and hold the entire signal all at once. Not like the FFT that we'd been working on before. Right? Very simple. But you kind of like that, right? So I'm thinking of a homework. Let's do a homework. Let's see. How does one do that? Content. Assignment. Okay, I think we're probably up to homework number 8. And what we'll do is we'll call this HAR wavelet transform. So we'll use an input audio file and do a floating point HAR wavelet transform show the first, I'll say 10 samples of the input file. The first 10 samples after the transform, and then the first 10 samples of the reconstruction. So effectively you don't really need to you do not need to play the audio file. Well, let's see. You do need to play it to know. You need to play the audio file to see if your program works. Let's see what else. You do not need to record the output as a part of your submission. So I do want to see that your program is working. So I would like to see some printout. as part of your submission. Oh, and here's what else I can do. What else can I do? I can put in some sample code here so that you can kind of see what I'm up to. I will copy it, copy, and put it into, here is some sample code that was done in class. You may use it if you like. If you like. Okay. Paste. So now you've got the sample code that I developed here in class. And what else do you want to know? Oh, and the other thing we did in class was we used the lifting in wavelets. So let's copy that. Put it in here. The integer lifting version of the code. The integer lifting version of the code is available from here. Uh-oh. Yeah, I guess that's alright. So you got a package name. You don't need the import, but that you'd want, I think. The other stuff, this is the code that was done in class. So here's the code. The lifting version of the code is here, and the code that was done in class is here. And that's everything we did in class today. What do you think of that? So that's 100 points, and unlimited attempts, and due in 1 week. And after that, I think we need to think about a final. So for the final, I'm thinking of a project. I don't want to do an in-class test. I want to give a programming assignment. So what I would like to do is brainstorm with you guys, but let me send this out first. And that's going. Gone. There's your code. What shall we do for a final? Any ideas? Suggestions? You guys are going to let me make this up myself with no input from you? You want to think about it? Well, I'm going to have an answer for you by next class. So think all you want. Send me an email. You know, give me your thoughts. And you know, you have to have a final. And I'm going to tell you something else about this final. When Thanksgiving is finished, okay, the end of the semester comes upon you incredibly fast. I mean, it's like lightning, man. So it'd be really good if we knew what the final was prior to the beginning of the Thanksgiving break, just so that we could have a chance to really think about it. So I would like to be able to announce the final and its content by this time next week, because you guys may need the time. You know, so it's a final of substance. And so I'm thinking that we should have you you know, something that we can sort of point at and be proud of and say, oh, look what we did in biomedical signal processing. What a cool idea. So I'll let you guys think on that. Can we do some real-time signal processing with the Arduino? Would that be fun? Yeah? I'm not getting the yeah, it would be fun look from everybody. Well, alright, I mean, you know, if you use the Arduino, it's not Java, right? It's C. But C kind of looks like Java anyway, so it kind of doesn't matter. I'll let you guys sort of think about it, okay? I'm thinking like a real-time equalizer in the Arduino would be fun. Wouldn't that be fun? I give everybody a sound board from my little Kickstarter project, and you guys can implement a little FFT. I think there's actually, I know there's a nice FFT library for the Arduino already, so you don't have to implement anything from scratch. And then you can proceed to do the equalizer that you had so much fun with in last week's homework. Did anybody have any questions about that homework? It seemed like a lot of people were not submitting any audio, so I couldn't really hear your output. The homework from last week, which we graded, I had handed in the grading electronically today. I graded it this morning, and I noticed there were a lot of people who kind of were missing like any audio, so I couldn't hear it. So I didn't know what you guys were up to.
Mine specifically, I didn't know where you had your audio files, so I created my own audio file that I had been using.
Oh, it's alright.
So you just have to, I mean, when you click play, it prompts you to select the file. And you just have to...
Well, I didn't like compile your code or anything. So I was expecting some sample input and some sample output so I could see how the program worked.
Yeah, I saw the note this morning and I went through my code and I want to like redo it. I wasn't liking the equalization.
Okay. Well, I mean, there is an opportunity to resubmit that particular thing, especially if, you know, you put in an effort but you didn't put in any sample input or output file, because I couldn't really tell what your code was doing by looking. Although when I looked at some people, you know, I could sort of see, yeah, there's problems here. Yes, sir.
You have to turn on resubmission.
I do? All right, so there is not. Okay, so what is the procedure here? I go into, I think it's homework 7, wasn't it? Oh, homework 6. Edit. Allow unlimited attempts. And then submit. So now maybe you can submit again. And then when you, you know, maybe I should give you guys a few days before I proceed to regrade. I don't know. You want to shoot me an email when you resubmit, or does it automatically? I don't think it notifies me. I don't get a notification when you guys upload.
You have 90 notifications. Top right.
Oh!
It's helpful sometimes to use that.
What's this do?
There's different tabs on the left. Fifth one down looks important.
Updates.
The one below that looks like
Retention. Updates.
retention. Yeah.
Retention.
Interesting. I didn't notice it existed.
Yeah, I don't really know what that does. Yeah, this is a whole area of Blackboard I've never seen before. There are updates? Oh, look at that. Missed deadlines. Oh, I can see everybody's missed deadlines. Did everybody here miss a deadline? click on this. No.
You know what? The
You
first
missed
two
it.
homeworks, a lot of us emailed them to you.
One deadline has been missed by more than 0 days. Missed 3 deadlines. View late submissions. Homework 1.
Yes,
Install
homework
Java and the Hearst exponent. Late for 35 days.
No. Oh, I emailed the early assignments too. That's right. I didn't see
Yeah,
that.
because
Yeah.
there was a whole problem. Remember, like
Right.
space submit
Here's an activity alert. Activity alert, 65% below. What's this? Doug Lyon. Oh, I missed my deadlines. What? Wait. Do I have to do my homework? I haven't been doing my homework. This is terrible. I don't understand it. What kind of a student doesn't do his homework? Well, that's very nice. I better keep track of that. Oh, maybe I should do a student at risk form for myself. All right. Well, I must tell you that I'm kind of a Blackboard newbie, and I don't know what I'm doing. But I have 8 students at risk, and I don't think I have that many in the class anymore. 8 have missed deadlines, and 3 students didn't contribute. I think I'm one of them. And 1 student didn't log in. Who's that? Oh, it doesn't say who that is. Oh, that's me. I've never logged in. This is terrible. Well, I must tell you that I'll have to talk to that Doug Lyon fellow. Yeah, thank you for pointing that out. Very productive, very interesting. Okay, well, that's all I have for today. If you have any questions about the home